Okay, so we are rolling, and so let's talk about some math here. Calculus 2. So if you're here in Calculus 2, that means you had Calculus 1, okay? And in Calculus 1, you were exposed to something called the fundamental theorem of calculus. Is that phrase at least familiar? It should be at least familiar. And this is one part of it, okay? So there's actually two parts of it. This is one part of it. And this should look familiar. But what I'm here to tell you is this is not just another formula for which you can do another set of exercises, okay? This is the fundamental theorem of calculus. Sounds important, right? And so this is packed with meaning. Individual parts have significant meanings. The whole thing has a very significant meaning, okay? And so it's possible that in your calculus course, you never investigated or explored the meanings, and that's what this is all about. It is not just another formula for which allows you to do another set of exercises in section 6.4 of the book, okay? It's the fundamental theorem of calculus. So we better understand what it is. And in Calc 2, much of the course is about, quote-unquote, integrals. And hopefully you know which side of this equation is an integral, left or right. The left side is an integral, and much of this course, Calc 2, is about integrals. Not all, but a lot. All right, so if we're going to be endeavoring in this course that's much about integrals, then we better know what this mathematical statement is all about, okay? We better know what the fundamental theorem is all about, not just another formula to crank out another set of answers to another set of exercises. So we're going to spend this first week really getting to understand what the fundamental theorem is about. Oh, that was all supposed to be, let's see here, how can I do this? I just made this particular slide before class. I didn't finish it, so we'll do it this way. Making sense of the fundamental theorem. So I'm going to break it down into a set of principles, something like 6 or 7. And so the first is actually principle 0, okay? Principle 0, before we can talk about any of the other main principles, the first principle is that variables vary, okay? Variables vary. So what do you think when you see this? 2x plus 7 equals 0. What do you think when you see that? Do you see subtract 7 from both sides and divide by 2 and then x equals? What? Hopefully we can do that in our head by now. 3.5, right? X equals 3.5. Could x be 4 or 10 or negative 0.5? Yes or no? How many people say no? How many people say yes? What are the rest of you thinking? Maybe? Okay, suppose that same x is defined as the number of hours elapsed since your plane left the ground. That's that same x. That's that same x that we just solved for as 3.5. Could x be 4? The number of hours elapsed since your plane left the ground. Could x be 4? Sure, 4 hours since your plane left the ground. Could x be 10? Yeah, could x be negative a half? Yeah, it could. How could it be negative a half? No. Half an hour before you took off. 30 minutes before you took off. Okay? This equation is just isolating a certain situation surrounding this topic such that x is currently taking on the value of 3.5, meaning maybe 3.5 hours since you got your first snack or your first drink on the plane. Not a great flight, right? Okay? So, just because we have this equation 2x plus 7 equals 0, x equals 3.5, if x has the meaning, say, number of hours elapsed since your plane left the ground, then x can take on any value. It's just that there's only one of those values that makes that particular equation true. Variables vary. So yes, x can be 4 or 10 or negative 0.5. It's just that when it is any of those values, that statement is false. The one value of x that makes that statement true is 3.5. Variables vary. We don't think of a variable as we're going to solve and get a particular value, and that's the only value it takes on. It takes on many values. Okay. So x takes on many values. In fact, any real number, if it's the number of hours since your plane left the ground. Okay, what would the variable dx represent? So dx is a variable also. That's a variable also based on the variable x. What would dx represent? I hear some people saying it. It would be the change in x, or in this case, a change in the number of hours elapsed since your plane left the ground. Maybe that's, so if dx was 1, it's possible. That would be some change of 1 hour since you left the ground. Maybe it's the change from half an hour to 1.5 hours since you left the ground. So that change could have been from x equals 0.5 to 1. And then 1.5. Then dx would be 1 hour. A change in that amount of time elapsed since your plane left the ground. Okay, maybe dx is 0.01 hours. So a very small change in time since your plane left the ground. And that can start anytime. That could start at x equals 0. That could start at x equals 5. That could start at x equals negative 0.5. Okay, principle 0. You have to see variables as they take on a real-world quantity, and they vary. They vary, and we might isolate a particular value of that variable, but variables vary. Okay. Principle number 1. Rate of change. Okay, now we're getting to the meat of it. So we got to have in place this understanding that variables vary. Principle number 1, rate of change. Example, you are buying trail mix that costs $3.20 per pound. After scooping some mix into your bag, you decide you want more. What additional cost will you pay for 1.5 more pounds of trail mix? Everyone figure it out to yourself, okay? Figure it out. What additional cost will you pay for 1.5 more pounds of trail mix? Go, figure it out. Okay, so just to set the ground rules here, whenever I give you a task this semester, and I will give you lots of tasks to work on, and sometimes you'll be talking with people around you, working on tasks, an option is not sit back and look at the screen. That's never an option. You're either making progress on the task or you're getting help. Those are your choices. You're making progress or you're getting help. Hopefully this is an easy task, but you're still going to do it. You're still going to do it. So I'll elicit volunteers today, but in this large lecture hall, we will be Calling on people. So, how much will you pay for an additional 1.5 pounds of trail mix? How'd you get that? All right, he took 320 times 1.5. And you got 480? Okay, so a very simple calculation that you all should have recognized and been able to do pretty quickly, but a very foundational thing in calculus. And so when we talk about it in terms of calculus, it's critically important that we have variables that are in symbols that are representing the thinking behind this. Okay, so let's do that. So we're going to define each variable below completely and precisely, and then define if its value is unknown or known in the given situation above. So here are all the variables we want to define in this situation: x, y, dx, dy, and k. Okay, and k is what we're going to use for rate of change. Okay, rate of change. Okay, so I will give you what x is. Okay, so what is x? X is the total number of pounds of mix in your bag. Okay, is that value known or unknown in this situation? Is the total number of pounds of mix in your bag known or unknown in this situation? I'm hearing mostly unknown, and that's true, that's unknown. Okay, so I want you to for the rest of these, I want you to define them like I've done, specifically and precisely, y, dx, dy, and k. And then for each of them, you're going to decide if it's an unknown or known value given what you have. And if it's known, what is its value? What is its value for at this particular moment, okay? And if you want to work with someone next to you and compare what you're doing or get help, that's fine. But those are your options. You're making progress on the task or you're getting help with the task. No watching the movie. Okay? No watching the movie. Go. Okay, what is Y? Yeah. Cost of X pounds of mix, or cost of the trail mix in your bag. All right, so what is DX? Change in? Oh, so do we know the total cost of the pounds of mix in your bag? We don't know it. All right, DX, the change in the number of pounds. The change in the number of pounds. In this particular situation, do we know that value? What is it? That's our 1.5. An additional amount, a change in the amount. All right, dy is the change in the cost. Do we know that? It is? And if K is the rate of change, what is that? It's your price per pound. Your price per pound, known or unknown? Known at $3.20 per pound, right? $3.20 per pound. Okay, so now I want you to, using the symbols, I want you to represent. So we solved, before we did any of this variable stuff, we solved this question. So now I want you to use the symbols that we just defined to represent how you compute the answer to that question. So when you computed that question, you just used values. Now I want you to do it the same way. Represent it with these variables that we just defined. Okay, what did we say? We said that 1.5, write it again. Or 320 times 1.5 equaled 480. So we want an expression that represents that particular computation. Okay, somebody new, volunteer. What would that be? Yes, ma'am.
K equals dx, or K times dx equals dy.
So she said that, and I'm just going to change the order. dy equals
K times dx.
K times dx. And this little statement right here embodies what we're talking about, constant rate of change. Constant rate of change. It costs $3.20 per pound. If we add an additional 1 pound, how much does our cost go up? You take 320 times the 1 pound, you get an additional 320. If we add 10 more pounds of trail mix, how much does our cost go up? $32, right? $32, because 320 times 10 gives us $32. So this is how we think about constant rate of change. It's not, here's the key. $3.20 per pound it doesn't only mean that 1 pound costs $3.20. From that rate, you also know how much 2 pounds cost. How much does 2 pounds cost? $6.40. How much does 10 pounds cost? $32. How much does 100 pounds cost? $320. So you can have any change in the amount. It doesn't have to be an additional pound. It can be any additional amount, and that constant rate of change will tell you how much more you pay. So this is our way of thinking about constant rate of change. Given any change in the number of pounds, we can get the change in cost by dy equals k dx. Any questions? Okay, new situation. Next, you remove 0.4 pounds from your bag and return it to the bin when no one's looking. Define each variable below completely and precisely. Decide if its value is unknown or known in the given situation above. Go. Take a minute. So our definitions stay the same. Do we know the value of dx? What is it? 0.4, is that right? Negative. A negative change means a decrease in the value of dx of negative means a decrease in the value of x, and that's what happened. The pounds went down, 0.4 pounds, so our dx is negative. dy. So let's go to k. What is k? Same. Therefore, dy is? What'd you get? Negative what? 1.28? Negative, right? Because it's going to be k dx, which is our 3.2 times negative 0.4 equals 1.28. Is that what you said? How can an amount of money be negative? How can an amount of money be negative? Yeah. It's a decrease. It's a decrease in the cost you're going to pay. So anytime you have a decrease, your change is negative. Okay? But it still follows dy equals k dx. Okay. New example. A soldier lowers an American flag from the top of the pole at 0.75 meters per second. How much does the height change from 0.6 seconds to 2.4 seconds since the flag left the top of the pole? Okay? If y is defined as the height of the flag in meters, define each variable below completely and precisely and state the value in this situation if known. Okay? So it's the same exercise again, but I'm telling you what y is. It's the height of the flag from the ground. Height of the flag from the ground. Okay, go. Define x. Y is already defined. Define x, dx, dy, and k. Okay, get a partner, work together, talk it out. You guys, start in the front. Come down. Start in the front and work your way back. Okay, let's see how you did. What is x? Okay, so we want to be specific. If you got something to do with time, that's correct, but we want to be really specific so we know exactly what time. The number of seconds I have since the flag left the top of the pole. Okay, number of seconds since the flag left the top. But something that's as specific as that. If you just said time in seconds, that's not good. We could define lots of time quantities in this situation. So time elapsed, or number of seconds since the flag was started to be lowered, or since it left the top. Okay, y we already said is the height of the flag in meters. So what is dx? Oh, let's go back. Is x a known value in this situation? Well, at one point it's 0.6 seconds, and then it takes on every time in between 0.6 and 2.4. So we could say it's all the times starting at 0.6 and ending at 2.4, maybe, right? So it's, again, its variables vary. It's taking on all those different values, okay? And then what about y? Known or unknown? Unknown. It's taking on lots of heights, right? It's taking on lots of heights as the flag descends. dx is a change in the time in seconds. Known or unknown? What is it? 1.8. You should have gotten 1.8. Final value of x minus the initial. dx is 1.8. Okay, dy. Change in the height. We'll go back to that. K is 0.75 meters per second. Negative. Why is it negative? Because our y is measuring height. Height is positive going up, right? It's increasing going up. If the flag is coming down, then that rate of change, it's just that y is decreasing. That constant rate is negative 0.75 meters per second. Important that you picked up on that. And so then dy is, we've got that, if it's in every second, it's descending 0.75 meters, then how much does it descend in 1.8 seconds? K dx. You're just going to multiply, right? You're just going to take negative 0.75 times our 1.8, and we get, one more time?
Negative 1.35.
Someone else get that? So in 1.8, so what does negative 0.75 meters per second tell us? It tells us a lot more than just in every second it goes down 0.75 meters. It tells us how far it goes down in any change in time. That number tells us how, if it's a constant rate of change at this formula then, and that value tells us how much it goes down in any change of time. 1.8 seconds, 10 seconds, 5 seconds. That's the key to this, constant rate of change. Okay, and so that was our dy. That's our dy, negative 1.35. Any questions? Okay, so here is, over there on the left, is a graph. How does it relate to what we were just talking about? How does this graph on the left relate to what we were just talking about? He said the line is showing the rate of change. Agree? So that blue line right there is at a constant value of what? Negative 0.75, right? And so this is a graph representing, on this axis here is, what variable is on this axis here? That's our x, our time elapsed since the flag started to be lowered. What variable is on the y-axis in this graph? Is it y? If it's negative 0.75 holding steady as x as time goes by, is this our quantity y, height of the flag? What is it? It's k, right? It's k. It's the rate of change. And this graph shows that it's constant, no matter what time's elapsed. When 3.5 seconds have elapsed, our rate of change is still negative 0.75 meters per second. That's what that point on that graph means. Look at this graph on the right. What could that be showing? Is that y? Is that the height of the flag as time goes by? No? Okay. Can you see that maybe this is a more realistic version of the rate of change of flag as it descends? That's what hopefully that's what you meant. Because what? Most of the time it's coming down at what rate? Negative 0.75. But then what happens? The rate slows to 0 quickly until it goes back to that periodically. What could that be about? It's changing hands. When you change hands, what happens to the rate of the flag? It slows to a kind of a pause for a moment, and then when you get to the other hand and you pull it down again with the next hand, now it's back to its rate. So this is showing the rate of change, maybe a more realistic rate of change. Pull, 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 okay? So we want to investigate, what was that question? How much does the flag descend? How much is its change in height? What was the numbers? From 0.6 to 2.4. And what variable am I representing right here? From 0.6 to 2.4, this duration right here is what variable? dx, the change in time. And we said that that was 1.8 seconds, right? And according to the constant rate, that ended up being resulting in the flag coming down 1.35 meters, right? Okay, what about over here? So now if I look at that same duration of time, looking at the more realistic rate profile, okay, there's going to be a difference because there's some positive. What is dx now? What is dx here? Still 1.8. So how do you predict dy will compare to the dy that we got over there? So we got a dy of negative 1.35. So now we want to find what dy, a more realistic value for dy. How much did the flag come down in that 1.8 seconds? Let's just predict. Do you think it's going to be less, more, or the same as, less negative, the same, or more negative than the dy of negative 1.35 meters? Less negative because some of the time it's going down at a slower rate, right? So in between hands, the flag slows down momentarily. So we expect a smaller negative total decrease, right? A smaller total decrease, or a smaller negative value for dy for how much the height comes down. So can we use k dx? Can we use k dx to do this? Not if dx is 1.8, right? Not if dx is 1. If dx is 1.8, what's happening? K is changing, and this is kind of like often in the real world, it's more realistic that a rate of change will change, that you don't just have constant rate of change. So this desk is one of the less frequent examples of what? Constant rate of change. But most things in life change at a changing rate. The rate is changing, okay? So what do we do here? What do we do? We can't just do a simple calculation, k dx, to get how much the flag comes down. But we still can use the principle of k dx. And what I'm going to do is I'm going to split up this dx, into separate intervals of 0.3 seconds. So from 0.6 to 0.9 to 1.2 to 1.5 to 1.8 to 2.1 to 2.4. Did I make a mistake in there somewhere? This is over there, like that. So I'm gonna break this down into intervals. I'm gonna look at smaller intervals. Okay? So in that first interval, what could we say the rate of change is in this first interval here from 0.6 to 1.9? Yeah, I mean, it'd be very, very appropriate just to say, oh, for that first interval, the rate, so we'll call it K1. K1 is negative 0.75. Why? Because it's pretty much constant at negative 0.75 for that. For that second interval, from 0.9 to 1.2. Now I want to be able to use this. So what do I have to do? I have to kind of pick a constant rate that kind of represents what's happening in that time frame. What constant rate would you pick? So it's what? It starts at negative 0.75, and at 1.2, it's something like 0. So pick something. Let's just make some kind of progress on this problem. So maybe what? How about negative 0.4? K2. Negative 0.4. So what am I doing? I'm kind of taking this changing rate function and making it into a bunch of constant rates. I'm making another function that's trying to be like this one, pretending to be like this one, simulating this one, but made up of constant rates. Then I can use dx, the easy math, right? Because now I've got all constant rate of change. What about in the third interval? It goes from 0 back down to negative 0.75. So what should we use? What constant rate? Negative, right? So we can use the same one again. It starts at 0, ends up at negative 0.75, so take something in the middle, like 0.4, negative 0.4. Okay? Next interval, K4.
Excuse me?
Yeah, please.
Why is it negative 0.4?
We're just anything to simulate it. Well, you could have said negative 0.35.
Well, wouldn't it be positive though because it's going down? It's a different slope now?
No, it's this is the constant rate of change at negative 0.35.
Oh, okay.
You see? So it's all the rates are going to be negative because it's never going to be going up. The flag's never going up. It's just in these pauses, if we're taking an interval of time over with these pauses, then we're kind of averaging it out. Does that make sense? All right, what about K4? What's a good, reasonable, back to negative 0.75? You see that? It's this thing down here. Okay, and then what about here from this to this? So here's where it starts. Here's where it ends. So actually here, on the average, it's kind of spending more time at a lower negative, right? It's not halfway between negative 0.75 and 0. It's actually spending more of the time up here in the less negative. So maybe negative 0.3. Do you see how I did that? But there's good estimates and there's bad estimates, but there's not right and wrong. Okay, so for K5, I'm saying negative what? 0.3. And then what about the last one? Negative 0.75 again. Now we've got what? We've got 6 constant rates of change over intervals of what? 0.3 seconds. Could you get an estimate for how much the flag lowers now in that total 1.8 seconds? Would you know how to do that? what would you do? You get the amount it goes down in the first 0.3 seconds, k dx. And then you get the estimated amount it goes down in the next 0.3 seconds using k dx. And then you do that for each of the 6 intervals. Find out what the little changes are, the little dy's, dy1, dy2, dy3, dy4. And then how do you estimate then the total change that goes down? Add them up, right? So then our dy estimate is going to be dy1 plus dy2 plus all the way up to dy6. And then we expect that to be a bigger or smaller negative than 1.35. A smaller negative, right? It ends up being something like negative 0.9. Anyone do it yet? If I remember right, with those estimates for k, I think it's negative 0.95 meters. Or something close to that. And that's just an estimate based on this changing rate function, a more realistic rate function. We have to break it up, estimate it with constant rates, and then get the total change by adding up the little bits of change for each interval. Okay. Written homework posted on Blackboard, due Wednesday at the beginning of lecture. If you have recitation this morning, you're going to recitation.